Hey everybody. Um, Great to see you again. Stat and I actually came to campus today. I'm back in my office. I was real excited to come to campus. Yes, true. Stat's never been to campus before. So we're going to work on some simulation stuff. You're going to tell him about me driving the truck? You did not drive the truck. You climbed on the steering wheel before you sat down in the passenger seat. You weren't. I was driving the truck. You weren't driving the truck. Okay, can we get on with this? Yeah, we're real excited because we're talking about stimulation. We are not talking about stimulation. We're not? No. Simulation. There's a big difference. Simulation, chapter 6 in our text, is trying to model the future. Model? Oh. So let's review models. What's a model? Simplified, idealized representation of a situation, problem, process, or object. Actually, Stat, you're a model. Because I'm beautiful? No, I wasn't thinking that so much because you're a simplified and idealized representation of an actual cat. I'm idealized. Well, I was thinking simplified more than idealized, but you go ahead and run with the idealized part if it makes you feel better about yourself. For our purposes, we talked about models are always wrong. Am I always wrong? Let's not go there, Stat. Models are simplified, so they're wrong. We talked about that early on. We took that same idea when we went into forecasting. The forecasts were forecasting models, and forecasts were wrong. And we talked about how forecasts actually constantly change, and models are often updated as things go on. So why do we do simulation? Why was I so excited? I'm excited too. Why are we so excited about it? Well, one of the problems we have with a lot of spreadsheet modeling and just mathematical modeling, way outside of spreadsheets, any kind of modeling done in the business world, is that it's very common to take averages as inputs and look at averaged output, and then sometimes feed that average into another model and another model, and it becomes a really cyclical problem. This example was created by Sam Savage back in the 1990s, brilliant researcher from the University of Chicago and Stanford. And his example kind of drives it home that if you look at the average position of this drunk in the street, on average, he's on the center line. So if you use that average as the input into this traffic model, it says that everything's fine. The average input is this spot. The average output is a living drunk. The problem, of course, is that he varies. The variability is completely ignored by looking at averages. And in reality, the average output is a dead drunk. A living drunk would actually be very rare. And if you don't necessarily like the drunk analogy, let's look at a manufacturing example. This file's out there on Schoology. Let me look. Okay. I've created a perfectly balanced manufacturing system. It's a 4-station manufacturing system. The first station feeds the second station feeds the third feeds the fourth, it comes out of the fourth, they're done. Stays production. It's a perishable inventory, so nothing's left over for the next day, just to make our lives a little simpler. But I said it's balanced because even though there's a randomness to the output, it's perfect. It's the exact same randomness. Every single station has this probability distribution of output. 5, 6, 7, 8, 9, or 10 with even probabilities. It's a uniform integer distribution. You could probably figure out that the average output is 8. Otherwise, you could do the mathematics and find the expected value. So all 4 stations, all 4, have the exact same distribution. It should be perfectly balanced. And if every station has a mean of 8, then the day should have a mean of 8. I created a what we call a single trial simulation model. We'll talk about those a little more in a minute. And we simulate with the ran between function, which we'll also talk about in a minute. Output, the capacity, I should say. So here's Monday, first day of the week. Station 10 was able to produce 10 units. Station 6 only had a capacity of 6 that day. Station 3, 9. Station 4, 6. If we average their outputs together, or their capacities, it's not that far off the 8 we expected, but the system only produced 6 units. This is the problem. This is like the drunk model. Yes, station 1 was able to produce 10, therefore it did produce 10. And it fed 10 units to station 2, but station 2 could only produce 6 units. So it only passed 6 units on to station 3. We lost 4 units. 4 units never got to station 3. Station 3 could have done 9. It only got 6 from station 2, so it can only produce 6. Station 4 got 6, was able to produce 6. We're lucky. Here's one where it's even worse. On average, across them, they had an average of 9. Only 7 came out. Same problem. Station 1 had a capacity of 9, so it actually produced 9. Passed 9 on to station 2, which could have done 10, but only had 9 to work with. Passed all 9 on to station 3, which only was able to do 7, only passed on 7. So even though station 4 could have done 10, it only produced 7. This is why we simulate, because if you looked at this and only looked at this, we might say, oh, well, yeah, we're going to get 8 per day. No, we're not. You can open this file, hit F9 a few times, and see if you ever get bigger than 8. We thought we'd average 8. Oh, there's an 8. Oh, there's a 9. The average, I'm pretty sure, is nowhere near 8. We'll actually find out that average later. So how do we generate random things in Excel? There's 2 main random generating functions in Excel: the rand and the rand between. The rand is a uniform 0, 1. And we'll go look at that in a minute. Theoretically, it's continuous. Really, it's not, but it's close enough to continuous for our purposes. And we often think of it as a probability. Sometimes we use it actually as a 0, 1, but we often generate it for, here's a random probability for the future. Rand between is integers, between A and B, any range you want, from 1 to 5, 1 to 6, -5 to -10, -5 to +5, 1 to 1,000. It'll do all those, and it'll do them uniformly. We're going to talk about F9, forces recalculations. When I talk, though, about random functions in Excel, we got to be careful, because computers don't actually generate random numbers. It's not possible. They do something called pseudo-random numbers. You need something that's physically random to generate random numbers, and computers don't have that. They use algorithms, computer programs, therefore they can actually be repeated, which certainly isn't random, and this we call them pseudo-random. We won't go through the mathematics. They're good enough for us. Again, you can actually do statistical tests to show that they act random, and and you can force what's called a random number seed to try to get a string of random outputs. But what it does, it actually pulls like 1/100th of a second off of the computer's clock, which makes it very hard to predict, although technically it's predictable. So let's see what these things look like. Open the example start function, and here's I'm simulating a coin toss. So I'm using the rand function to generate a random probability, and if the probability is less than 50%, it says head. If it's greater than 50%, it says tail. Fairly standard way to simulate a coin flip. Whether or not you'd put all this in 2 steps or in one function, it's a different issue. We talked about that way back in chapter 2. This version, which just has the output, it takes up far less space on your worksheet and is simpler to look at, but it did add one small complication to my function. Which of these is better? Do it in 2 steps or do it in 1 step? There's not a better. It depends what you're trying to accomplish, who's going to look at your spreadsheet model, what you're going to do with your spreadsheet model, all those things. Well, what if you've got an output that isn't 50-50 like a coin? Well, you can feed a value in. So I just made up that we have a situation where 10% of our customers are angry, and we're going to randomly simulate a customer. So if this is less than 10%, less than or equal to 10%, we say they're angry. If it's above 10%, we say they're not angry. And this should work out that 90% of the time, we should be getting a not angry. And about 10% of the time, getting an angry. So How do we do that? Instead of saying if it's less than 0.5, if it's less than this value. Same idea. A couple of fairly standard uses of the rand function. Rand between. It's not hard to simulate a six-sided die. Just do rand between 1 through 6. Or if you want to do a pair of dice, first die, second die, sum of the dice. Rand between is really good for a situation like that. Once you kind of get a feel for how these things work, you can twist them more and do more with them. Let's say I want to generate percents. Now, first of all, from a chapter 2 perspective, if you look at this sheet, you're going to see a lot of hard-coded values in the formulas. Again, it's not necessarily a good idea, but I did it here to try to let you focus on what the rand function is doing and what's happening to it. So I want you to look at this one on your own and look at the formulas. But if I need to get a percent between -5% and +10%, so it's an investment that could lose money, could make money, and I want to randomly generate what's going to happen in the future. Well, I randomly generate an integer between -5 and 10 because rand between only does integers. Then I divide it by 100 to make it a percent. So in this case, 2%, I'd have $5,100 on my $5,000 investment, $5,450 on my $5,000 investment. I'd lose money. The problem with this, it does work, but it's still a fairly simplistic simulation because I'm only getting essentially integer percents. The only possible percents I can get are right there. -5, -4, -3, all the way up to 8, 9, 10. I can't get 3.8%, 7.5%, no tenths of a percent. If I want tenths of a percent, I got to think a little deeper. So instead of generating an integer between -5 and 10, an integer between -50 and 100, then I divide by 1,000. Of course, now I can't get hundredths of a percent or thousands of a percent. So whatever precision you want, you may have to modify this process. But it does show you that you can use this integer generator to do some things that aren't integer. Other things you can do with, well, we'll jump over with the rand between. It's called bootstrapping. Sometimes you want to randomly pull data out of your existing data. Whatever you've got doesn't fit any kind of theoretical distribution. So you just want to say, here's what I've got. I'm going to pull out of this. Well, over here, I'm using a rand between. So I take my actual data, I put an integer index on it, and I use the rand between function to generate a random index value between 1 and whatever my top value is. And then I use a VLOOKUP. Remember VLOOKUPs? We talked about those before. To find, in this case, the 16th, sorry, the 16th person in major, or whatever I'm looking for. 14, Jordan Finance. 16 again, 2. Pretty handy tool for doing that kind of work. Discrete distributions, excuse me. Instead of a continuous distribution, let's have something that's set 4 outputs with these probabilities. And I want to randomly generate one of those for the future. Well, first you kind of flip them. There's a reason for that mathematically. I don't really need it in a lot of ways. So you get the outputs at the end and those individual probabilities. Then you create, it's kind of an offset cumulative probability distribution. So it's kind of 0 to 5% is 100. 5 to 30% is 300, which is, or sorry, 5 to 35% is 300, and right on through. So above 60% is this. How does that work then? You generate a random value and you use the VLOOKUP again. And it says that based on 17.5%, you're between these. So that's this next 30%. It's a 300. 75%, you're between these, between 6% and the end of the distribution, so it's 650. 53%, you're between these, between 35 and 60%, so it's 400. And it's the first VLOOKUP that you've seen me use where I use true instead of false, where I'm getting an approximate instead of an exact lookup. It's an example of where you actually would use that. Now this works whether the output is numbers or words or whatever. This is still a discrete distribution. So those probabilities, there's the probabilities. You create the cumulative probability. You can look at the formulas I use there. You randomly generate a probability, and it tells you what class in this distribution you have. We went to bootstrapping. Last thing on the distributions, any continuous distribution has something called a PDF, a probability density function. And that's the function that actually creates the various curves you see for probabilities. And if you can randomly generate a probability and find the mathematical inverse of the PDF, you can generate anything from that distribution. Now, with normal distributions, it's not too hard. So let's just say we want to randomly generate one output from a normal distribution with a mean of 10 and a standard deviation of 4. In that probability, I can actually just use the norm inverse. I don't have to know the PDF for a normal distribution function. The norm inverse function puts in this probability, puts in that mean, that standard deviation, and says, okay, here's a random output from a normal distribution. I can get a bunch of them. The exponential distribution, you may not have seen much of in your classes. That's used to commonly model inter-arrival times between customers into some kind of service system or manufacturing system, queuing, line waits, line systems. Doesn't really have a standard deviation, just has the mean. I'm not going to make you go look up the function. We may talk more about this function if we use it, but it's interesting here. I do have, it doesn't look like much, but the mathematical inverse of an exponential distribution. So you get a probability. That's the normal logarithm or the E-based logarithm. And again, we're not going to go through the mathematics of it for now, but it works. So there's a bunch of different types of distribution you can get just using those two Excel functions, rand and rand between. So how do we actually build a simulation model? Because I haven't done that yet. I've just shown you not even step one here. The process for building simulation models is that we are going to go into the spreadsheet and create a model. It's going to look a lot like a chapter 2 model, except it's going to have random components. That's what we call a one trial. That's like flipping the coin one time. Once that model's working and we're confident that it's working, then we go and simulate a bunch of trials, many trials. How many? As many is can get fairly complicated. We can do calculations on changes in margins of error if we want to get really statistical. But for what we're doing, 5 to 10,000 tends to work out pretty well, and the computers are powerful enough that that's not really a problem at all for our computers. Our computers could probably do 500,000, but that's overkill, so we won't go that far. And we're going to do something with data tables. So we're going to review data tables too, because it's a pretty cool use of it. And then once you've done, here's my single trial, here's a bunch of trials, then we actually analyze the results of the many trials. It's pretty much traditional descriptive statistics. Then we draw conclusions about our situation. So what should you focus on today? Well, we've quickly reviewed modeling in general. Figured out that I'm a model because I'm beautiful. No, you're a model because you're simplified and idealized. Okay, fine. You're idealized too. We spent most of our time today generating random outputs in Excel. I didn't really talk about this model building process yet. So the one trial simulation model, here's a problem we've looked at. We already looked at this auction problem from chapter 2, where seller had a reserve price, there's a commission rate, there's a weird buyer's premium, there's a listing fee that for us didn't do much. And the key was, what does it actually sell for? What's the winning bid? We figure out, did the house make any money? So if the winning bid was $50,000, House would lose money. If the winning bid was $90,000, the house would lose money. Sorry, make money. So instead of just playing that game, what if we had a probability distribution for that? And that's what this is. See if you can figure out how to take that spreadsheet and replace that input with a random input. Try two ways: a uniform distribution between 50,000 and 150,000, which you'll note has a mean of 100,000. And then try it with a normal distribution with a mean of 100,000 and a standard deviation of 16,500. That won't have exactly the same boundaries as this one, but that's once you get 3 standard deviations above or below this mean, which is about where these are, you're not going to have a whole lot of stuff outside of that. So these are remarkably close in terms of their range and their mean, not the same standard deviation. And just see if you can get the mechanics of that working. We'll do a simulation with that later. This isn't doing the simulation, it's just getting that first trial built in.